Hi, this is Paul Schreiber of Synthesis Technology. This video is the hardware schematic section of the Midiverb 1 teardown. There will be a following video which talks about the software side of it and the algorithms. Today we're going to talk about the actual hardware. This is a schematic of the Midiverb that we reverse engineered from the previous video, and it's drawn in a CAD program that I use for both schematic and PC board layout called DIP Trace. So this is not a PDF, this is live. As you see me move my cursor around, you'll see different nets highlight and like light blue and things like that. I can actually double click on a component and it'll bring up the component and who makes it and the footprint of the PC board pads. So let's get started. We're going to start with the power supply, which is very unique. I've never seen a power supply like this at any piece of electronics effects gear, or most gear for that matter, because it uses a center tap transformer AC wall wart, which has 3 pins, and the center tap is ground. The jack that's used is a Molex 156 MTA connector. Again, I use those on my MOTM power supplies, but that was all internal wiring, not exposed to the outside world like this one is. What's also unusual is you would not expect to see 6 diodes and 2 capacitors essentially in series with the AC line. So let's find out what makes this power supply pretty unusual. We'll start with the +5 supply. Now the +5 supply, which is a 7805, this is the high current supply. It's around 325 milliamps. We're all familiar with these 3-terminal regulators. The thing about 3-terminal regulators of this type, they're not LDOs. That stands for low dropout. This is high dropout. You have to have at least 2 volts differential between the input and the output voltage. So we would need 7 volts minimum here, and we have to have at least 14 volts here and here for the 12 volt regulators to work. On the 5 volt supply, if we just ignore these outside diodes and look at CRs 3 and 4, this is a classic full wave rectifier with the center tap. So on the positive cycle, this diode conducts. On the negative cycle, this diode conducts. And you have these large filter capacitors, your 5 volt regulator, and out. Since it's using the same transformer, it has to have the same voltage essentially here and here and here, we think at first. So this is on a heat sink. This is going to dissipate a lot of power. Now let's look at the plus and minus supply. Well, usually when you have a center tap transformer, that's also fairly easy to do, except why do we have these capacitors in series with 2 sets of diodes back to back here, and only one goes to the ground reference and the other one's coming in? So you think of, you have a positive cycle going here and the negative cycle coming back through here, but why in the world do we have to put it through a capacitor? We don't do that on the +5. And the answer is, this is a voltage doubler. And the reason you say, wait a minute, why does he need a voltage doubler? Well, he wants to have the lowest DC power dissipated in this part here, the high current part. So he only needs 7 volts here, remember, but if he wants 14 volts over here, the way you can get that, especially if it's lower current, and remember, these parts are just driving op amps, is use a voltage doubler. So you can get twice the voltage with half the current. But you don't care about the current in this application. It's probably 20 milliamps. So he uses a voltage doubler, so we can use the lowest AC transformer here and still get that 14 volts he needs there. And that's pretty clever. And this was fairly common back in the 80s. I actually used this exact same technique on a modem I did for Radio Shack when I needed to have plus and minus 12 volts just like this. And I used a voltage doubler. I didn't use a center tap transformer. I just used an AC wall wart. But it's a quick and dirty way to get bipolar supplies with a lower AC voltage input. The next page of the schematic is going to be the analog filters for the input and output stage. The first thing to notice about this is even though we have our 4 jacks, we have 2 left and right coming in and 2 left and right going out. This is not true stereo. They're summed right here between the left and right channels. So we have a single audio input and we do have separate left and right outputs. So that was the first thing I noticed that was kind of misleading, I'll say. It's very common because back in the 80s, you couldn't have dual DSPs running the algorithms. And so you simply had fake stereo. And we'll talk about in the software section how you actually faked out that stereo. You have one control on the Midiverb, which is this dual gang mix pot here between the dry inputs and the wet signals. Nothing special there. I'm going to slide this over and zoom in a little bit. Bear with me. So let's just talk about the filters. The input sides are identical. You have this AC coupled input stage with this 150 puff across the input. That 150 puff cap is for AM radio suppression. Remember AM radio? Well, it used to be a big thing in the 80s. And if you didn't put this cap in there, the ESD diodes of the input stage would sometimes rectify AC signals because that's what an AC detector is. It's a rectifier and a capacitor. That's all you need to make it, remember crystal radios? So we don't want a crystal radio using our ESD diodes, so we put this capacitor here. Now this capacitor and this resistor is 2 functions. All right, the first one is we want to have AC coupled inputs, and we have to have some kind of relatively high input impedance, in this case 51K. But usually you put a larger value here, and this value here is kind of high, it's 0.1. You may have seen 1 or 10 microfarads, because we want a specific high-pass filter. So why is there a high-pass filter here? It's just to get rid of any kind of low-frequency stuff. We call it a rumble filter in turntables, but it's generally a good idea to have something that everything below 50 or 60 hertz is filtered out. I'm going to zoom up here a little bit. So let's talk about the input and the output filters. If you know anything about digital signal processing, is that you have to have a band-limited input. You can't just take the audio straight in and sample it. You have to have it below the sample rate. And so what we're going to do here, we're going to have a 2-stage filter, a 4-pole filter, and we're going to do 2 things. This is going to roll off our input bandwidth below the sample rate. Ideally, you want all the audio coming in to be less than half the sample rate. And it also does what's called pre-emphasis. Now, pre-emphasis is something that was done in cassette recorders. And what that means is that you're going to boost the treble on purpose on the input side because you know that the playback side, in our case, our D to A system, is going to attenuate high frequency. And so to make it a, quote, flat response from input to output, you boost the highs going in. Now, you could say, well, why boost them on the input side? Why don't we boost them on the output side? And the answer for that is because that was going to boost not only the audio, but the noise generated by our D to A converter. And since this is not an oversampled system like we have today, this is a baseband system, we'll talk about that in a minute, you have to use pre-emphasis. And it turns out that there's a lot of pre-emphasis in this. And it's split into 3 filters. The second one here has the main cutoff frequency with the first pre-emphasis peak, 10 dB, around 8 kilohertz. That's the high end of the piano range. The first one is not exactly the same. It's cut back a little bit. And the reason you do that is you're doing a little bit of hand waving so that you can try to get a little bit more high frequency attenuation by having this one roll off a little bit sooner than that one. This is a system that samples are in the 20 kilohertz range. I think it's like 23.5 or something exactly. And that's pretty low sample rate. And so you're trying to get as much audio through without getting the aliasing through. We'll talk about that again in a second. These are standard Salwin key filters. You can look them up, and I'll show you the response of the entire input and output stages in just a second. Let's talk about the output stage. I want to just kind of center that and zoom in a little bit. So they're identical. We have left and right. I've shown the sample and hold capacitor here as opposed to the other schematic. So there's an analog switch here. There's an analog switch here. And every so often, it has to be at least the sample rate, but it can be higher. We're going to charge this cap up from the DAC, which will be a DC voltage dumped onto here. And then we're going to try to take that DC voltage and make an audio signal by passing it through this low-pass filter network. It's in two stages. The first is a very high cutoff right here that's passive. Why he picked this magic number, I don't know. It's approximately, 2 octaves above the sample rate cutoff. So it does some really high frequency roll off, but most of the high frequency roll off is this single stage 2-pole filter right here. All right. It's set at 11 kilohertz. I say mostly flat. There's a little bit of ripple in it. It's a Chebyshev response, but generally speaking, it's actually set about 2 kilohertz back behind half of the sample rate. And again, it's a game you play. The more you pull this cutoff frequency lower and lower, the more the high frequencies are attenuated. Now, I know Keith Barr was a brilliant designer, but I think this is where he made a mistake. All right? He made a mistake because he was trying to save the cost of another filter stage that you would put right here. He should have had a 4-pole filter just like this one, the same topology, different cutoff frequencies and responses. But he said, you know what? I just don't want to do it, or I may not have room. This is the only thing that I think he did incorrectly in the Midiverb. He should have put a 4-pole filter on here. And the reason is that since this is a baseband system, meaning that at the sample rate, again, in the 23 kilohertz region, all right, since we don't upsample, which we do in modern converters, which means that we take the basic sample rate, say it's 48 kilohertz, we're going to actually pass that to another digital signal processing stage called an FIR filter, and we're going to what's called upsample that by 256 times so that the effective sample rate, not what we actually sampled at, but what the audio spectra of the result is, it's like we had a 4 megahertz sample rate. Well, that's easy to get rid of with simple low-pass passive filter that's used a lot of times, like in our 520 Hyperion. It's just a simple passive filter to get rid of the upsampling. But here we're not upsampling. So what does that mean? That means that at the output side here, we're going to have a lot of that sample frequency in there. Because at this point right here, before the filter, it's at 0 dB, which means that it's at full scale signal at 23 kilohertz. Well, what's it going to be out here? Well, it's still going to be there quite a lot. And here's an audio precision plot of what the result is. If you put it in bypass, theoretically, you shouldn't have any signal, but here's the signal that's there. And you could have greatly attenuated that by having one more stage of filtering, which he did not do. So now we're going to talk about the D to A / A to D, because it's a dual shared system converter, the sample and hold mux and some LEDs, and the last audio filter. So let me just kind of zoom in here. We'll first talk about the top part of the schematic. This is a CMOS triple 2-to-1 multiplexer, which is used as 3 analog switches for the 3 sample and holds. Why 3? You have 1 on this mixed audio input and 2 for left and right. This is the last preemphasis filter that comes in. So On the input side, we have a 6-pole filter. This one has a higher cutoff with a much higher peak. And I'm sure this was all done empirically and done by ear and what sounded the best. But it turns out we have a lot of preemphasis. And so here is a SPICE simulation of the total signal chain on the input side. This has the 3 LEDs that are on the front panel. There's a clipping LED and some level indicators. Pretty straightforward. So the clipping LED is kind of unusual. One side is tied to +5 through this 1K resistor for the current limit. The anode is tied right here to the op amp, which is the same as the output side because this is just a buffer. And I'm sure this was done, again, strictly for ease of PC board routing. So this is biased up here, so in order for the LED to turn on right here, okay, it has to be at least the forward voltage higher, which is about 1.5 volts. So this thing starts turning on about 6.5 volts peak. And when it gets, you know, up to like 8 volts, it gets really, really bright. It says that you're really, really clipping. So this is where he sets the level, right about here, which is the same level as here. The other level indicators are simply transistors that are set by thresholds. There's a little bit of RC time constant on this one to have it kind of, you know, not blink. This one's going to blink. This one's just going to be kind of laggy. Let's scroll down here to the D to A and A to D section. So this is a standard 12-bit part. It's from AMD, which is kind of strange. People don't remember much about AMD, but when they started, they were an analog company and not digital at all. And so this is a 12-bit DAC. The DAC has differential current outputs, which is important because that's an easy way to get bipolar audio output signals without level shifters. It does run on a plus and minus 12 volt supply, which is unusual as well. The current outputs are converted to this by this differential amplifier here. With this is the gain. So this is your master audio gain right here. You can also do some makeup gain in the output filter. And so the voltage that's here, that the output audio is coming out, is equal to the current times 2400. And that current is set by this resistor here, tied to VREF. It's actually IREF, but they call it VREF. And so this is how you set your output voltage. There's a trim pot here that's for mid-scale, which would be 0 volts. So you would have to force a mid-scale here, which how do you force a mid-scale? All of these are zeros and the upper bit's a 1. And then you adjust that for 0 volts out. What's this comparator doing here? This is an LM311 high-speed comparator. Well, this is how we turn our D to A into an A to D. And so how that's done is there's one extra chip that's needed over here that's on another page of the schematic called a SAR, Successive Approximation Register. And this SAR is essentially a little pre-programmed state machine that outputs a binary tree search in these data lines based on the status of this ADC comparator line, which is fed back to the SAR. So if you look at the comparator, it's looking at the audio input, and we'll call it the audio output for lack of a better term. And when the comparator says this voltage here is higher than that one, I'm going to be a high. If not, it's a low. And so the way that you make an A to D converter is you put a specific count here, and the count happens to be we're going to set the MSB first and set all of these to 0, which is mid-scale, and you see if the audio coming in is more or less than mid-scale. And you do that by looking at this bit. And let's say it's a very small voltage, it's going to be less. So the SAR register keeps that bit from a 1, it flips it to a 0, and sets this bit, and checks, and so on. So it sets to a 1 and flips to a 0 if it doesn't get a value. And as it goes down the chain, at one point it will flip up and say, oh, you're too low in voltage, and then it will stop and keep flipping these bits all the way down until it does 12 tests. And so after it does the 12 test, the result here is the analog value of the input voltage. And that's called the SAR converter. And this is still today the most popular way to make an A to D converter. You can run these very fast. It's not uncommon to have microcontrollers that have 1 megahertz A to D converters on 16 channels, and they're all using this exact same technique, all done inside the part. So now we're going to talk about the digital side of the Midiverb. The first page we're going to talk about is the microcontroller and the actual DSP EPROM and program counter. So I'm going to zoom in on these various things here. Bear with me. All right. First part of this will be the MIDI input side. This is very standard. The MIDI part of the Midiverb is only one function, and that's a program change. And that's how you tell it which algorithm to select. So there's no transmission of MIDI. It just takes MIDI in through a standard optical coupler and a couple of transistor level shifters to generate our MIDI in and our MIDI through signal going back. So it's very simple. Start with the clock. I always like to start with the clock. The basic clock frequency of the Midiverb is 6 megahertz. So this is the oscillator circuit. It uses a ceramic resonator instead of a quartz crystal for cost savings. Ceramic resonators came out in the 80s as a low-cost alternative to quartz crystals, and they were about 15 to 20% of the total price. So they were widely used when the frequency doesn't have to be exact. Ceramic resonators have about a 3% accuracy versus 0.005% for a quartz crystal. So the base frequency that the Midiverb runs at is 6 megahertz for all the digital logic and for the processor. Again, the processor, all it does is scan the front panel buttons and look at MIDI and drive the 7-segment display. So it doesn't matter what speed it runs. We'll zoom out just a little bit here. And I'm going to zoom in just on the processor section for now. So the processor is a 80C31. C means CMOS. So this is a microcontroller, 8-bit, 12 T-states machine. So this thing is running at 500 kilohertz internally. Again, not very fast. It uses an external EPROM here. This EPROM, one of two, has the 8051 code in it, and it's probably using only 5% of the space in the EPROM. The 2764 at the time was the cheapest EPROM you could buy. That's why I used it. So you need 3 parts in an 8031 system. You need the processor, an EPROM, and this 8-bit transparent latch because the address and data bus are multiplexed. The addresses come out first. So when the addresses come out, this transparent latch flows through to the EPROM. When ALE is asserts, that stands for address latch enable, then the addresses are frozen over here, and it's just the lower 8 bits. The upper are not multiplexed. They're on port pins. We'll talk about that in a second. So the lower 8 bits are latched over here, and then the data comes out on the same bus over here where it says AD. So that's the data bus. So this is very common multiplex system. The 8031 microcontroller has what we call 3 internal ports, ports 1, 2, and 3. And if you see on the schematic, they're labeled with different functions. This is because the 8031 was the first microcontroller that had dual function pins. Now, if you look at the ARM microcontrollers, they can literally have 20 functions on one pin. But these only have 2, thank goodness. And you can see, let's look at port 1, for example. This can be an I/O port. We call those a GPIO, general purpose input and output, which means the software can just say set it high, set it low. or it can be tied to a function inside. For example, this is the timer 2 clock input. So the software has to set these bits up when it boots up. We use all of these generally as individual GPIO. The only one that's not a GPIO is when we do the MIDI in. And if you look at MIDI in, it's tied to receive data input on the UART. So the software will say, for this bit on this port, this is going to be our receive data input for the UART, but it's bit assignable. And so these have the second set here, okay, of pins. And so you can see these are interrupts right here. And so you have channel up and channel down. That's the push button switches. And so that's easily a way how to do that. On this side, we have just I/O ports. We'll talk about that in a second. Now, in most microcontroller systems, you have many things that you can input and output. And so those are called external ports. So we have both internal ports, but external ports in the software. So these are dedicated addresses, but we have open addresses that we can do in the software to address lots of I/O. And so when you do an import or output instruction, you have an address and data. So the address will appear on the address lines, data on the data lines, and then you have the read or write as asserted. And so you have external logic called an address decoder that says, I want to write to port 23, I'll look for address 23, and a write signal, that means I'm writing to 23, that's for me. The Midiverb only has one single external port, and it happens to be all the ports. And that's this write signal here that goes to this 8-bit latch to drive the segments for the displays. Okay, so in the software, you can just say write to port 59 or whatever port you want. And no matter what port you write to externally, it's going to write to this data latch. So that saves some money there. There's no address decoding. And since he doesn't have to read anything, because he has enough pins on the processor not to use an external port, let's talk about the 7-segment displays on the front panel. There's these two old Monsanto. Monsanto invented the LED. People think they invented Roundup, which they did, but they also invented the LED, so we'll give them credit for that. So these are old Monsanto LED displays, 7 segments. They're called common anode, which means all the anodes of the LEDs are tied together, and the cathodes are brought out on separate pins. That means that you apply a voltage here, and when you pull these pins low, the segments light up. And the reason you want to pull them low instead of push them high is that in the early days of TTL, they could sink a lot of current, but they could not source a lot of current. So it's much easier to pull things to ground as it is to try to push things up to TTL high. There's 2 displays, so they're what we call ping-pong multiplexed. The software rapidly is selecting one or the other, and that voltage, the +5 voltage, is applied to these PNP transistors. So these are going to be active low signals for each display. So the software, for 99.99999% of the time, is simply going back and forth on these displays and putting zeros here when they want the segments to turn on. Now, that's not very exciting. I'm sure you're thinking, well, I knew that. But when I did the reverse engineering, this is literally the first circuit I did was right here. And that's where I discovered that Keith Barr is a sneaky little guy. Because what most people do, even though you don't have to, but this is just what you wind up doing mentally, is when you have an 8-bit data bus here with 8 outputs, and this is called D0 on the data sheet. You just say, I'm going to take D0 over here and hook it to D0 out of the processor, and 1 to 1, and 2 to 2, and 3 to 3. Now, is that a requirement? No. No. These are independent flip-flops, and we don't even know how they're built on the die. The data sheet just called them that. They could have called it D309 and D417. It just doesn't matter. But this is just what we call de facto nomenclature. And so what most people will wind up doing is simply hooking them up 1 to 1 and 1 to 1. And then you come down here, since there's 7 segments called A through G, why not hook them up A, B, C, D, E, F, G? The argument can be, well, you don't have to do that because the processor over here doesn't know what you're driving. So you have to have a lookup table anyway. So if you want to put the number 2 on the display, you have to tell the processor what zeros to drive to turn the segments on. Who cares what the bit order is in the table? The answer is you don't care at all. But it's just unusual not to do it on the board. And so what I discovered was he did this to make the PC board layout easy for him. It's a double-sided board. He wanted to minimize the cost. He wanted to minimize the time. This is hand routing, no CAD. So he basically hooked it up any way he could, and then he went back and changed the table to match what he routed. That's not normally done. You normally route to the table. And so that's an interesting thing. And when I figured out that's what he was doing here, that he was, scroll this in, you can see it doesn't go, you know, A, B, C, D, E, F, G over here. If you look at what the drive signals, it doesn't go A, B, C, D, E, F, G over here. That's what I talk about a scramble. You would expect this to go A, B, C, D, E, F, G, and so on. So these bits are scrambled, which means they're scrambled over here, but you would expect this to go like 0, 1, 2, 3, 4, 5, 6, 7, and it doesn't. And I said to myself, what's going to happen is if he did this for something as simple and basic as the LED display, he's going to do this all over the board, and you have no idea. I'm now going to talk about this little section here. Let me just zoom in a little bit. All right. Remember I said there's an EPROM here and an EPROM here. This EPROM, which is much larger, you can see it's twice as big. It's completely full. And this one contains the DSP instruction set. So this EPROM only has the instructions for the 8031. This EPROM has a completely different set of instructions for the DSP code. The way it's done is pretty clever. So we have 63 programs in the Midiverb plus a bypass. And of course, the bypass is a program. So there's 64 programs. And each program is exactly split into here into 64 equal parts. And if you look at the address lines, you can tell exactly what's going on. You have what we call program select on the upper ones. And there's 1, 2, 3, 4, 5, 6, which means we have 64 selections. So we can call this, people also call this as a bank select. And these are driven from port pins out of the processor. So when you push the front panel button, our MIDI command comes in that says, I want to see algorithm 17. You put binary 17 right here. Notice he didn't scramble it. Good for him. He puts binary 17 here, and it's going to index into the 17th program block. The lower bits here, okay, this is 0 through 7. So you have 8 bits, so you have 256 instructions, and they are connected to these up counters. So this is our program counter. So what happens is at the 6 megahertz rate, this thing is scanning through the EPROM over and over in a loop. There's no jumping, there's no go-tos, there's no conditionals. We're scanning, scanning, scanning in a loop and dumping those instructions out on the DSP data bus based on the program number that we've picked. Now, there are a couple of exceptions. I want to zoom out, talk about the way that the software is written. It's at certain address locations are tied to a function, so that anytime you want, for example, load the DAC to put a voltage out, all right, for an audio conversion, that's tied to an address, and so that's just toggling that function, all right? There's also some things to do with the DRAM timing, which is this flip-flop down here. We'll talk about that. But in generally speaking, this is just a fixed program counter running 6 megahertz, so we have a 6 megahertz instruction time running through the DSP algorithm right here. On this page, you have essentially the Midiverb DSP engine. And so it's fairly complicated, and it's a little bit squirrely down here. It kind of makes me cringe when I see this down here. But we're going to talk about what's going on. So let me just zoom in. Now, this discussion really is coupled to the software side, which is the next video. So you may want to wait and kind of watch them both, and maybe even watch the software one first. I don't know, it just depends. Because this engine is specifically designed to run his microcode. And that's typical for all DSP processors up until the TI 320 series, which were general purpose DSPs. This one is not general purpose. Every single part in here is designed to run only his 4 opcode instruction set and only run these algorithms. It is not, quote, general purpose. It is just for the Midiverb. Here's what's going on. This is what we call a MAC, multiply accumulate. Now, multiply accumulate is the basic instruction for all DSP. It means you take a value in the accumulator register, and we're going to multiply it by a constant that comes from the coefficient memory, and then we're going to add it back to itself and stick it back into the accumulator. So that's called multiply accumulate. Well, we don't have a multiply instruction here. What we do instead is we have adders. And so what we're going to do is we're going to do an effective multiplication by fractional adding and subtracting to, quote, get the right answer, right? Because if you multiply 2 times 3 to get 6, that's like adding 2 plus 2 plus 2 3 times, right? That's like the definition of multiplying. It's successive additions. If you multiply times a -3, right, you add and do what we call a sign extend. And so this is what this little DSP does. All right. So we have an accumulator. We have an internal pipeline storage register that feeds the adder. We have the result here, and we can feed this back here. So that's our accumulator, quote, multiplier, store and feed back. All right. We also have pipeline registers for the input side. When we're doing an A to D conversion, we have a separate set of pipeline registers here when we're doing a left and right DAC output. So these registers, the DAC outputs and the accumulator, are mapped to certain addresses inside the block of the program. And this is all mapped down here. All right. We also have a saturation and sign extend down here. So we have 12-bit system. So we have 16-bit wide. We have a 16-bit wide accumulator with a 16-bit wide memory. So we have 4 bits of what we call overflow. So that means when we do the math, we can have essentially a result that's plus or minus 8 times bigger than what we started with. And of course, It's a 12-bit output, so we round that down to 12 bits at the end. So we have what's called a saturation here, which means are we getting close to overflowing in a 16-bit word with our math? And the answer is yes or no. And so it says it's true when the top 4 bits are all 0 or all 1s. So that's what we look for. We do underflow, the lower bits are 0, overflow, the upper bits are 1. And so this logic here decides to do what's called a sign extend right here. Remember I talked about we have different instructions in the block, mean different things all the time. All right. And when I say instructions, I mean like when we input from the A to D and read and write to the DAC, that's always a constant offset. And this is what this instruction decoding timing here does. So it triggers the sample and holds a cycle early because we want to have the sample and hold settle before we actually read the result. So that's pipelined. Since we're having dynamic memory, we need to have CAS and RAS, and we have what's called the famous Don Lancaster monostable, where we have RCs and inverters to make a time delay, because if you look through here, we're taking a single signal right here, okay, and both clocking and presetting the flip-flop from one signal. Well, we have to have a setup time from the preset to the clock to get the signal. So we feed the preset going forward, so it has a setup time, and we go delay some more. Okay, clock it in. Okay. So that's the preset and the D signal coming in. And so when we're going to, first we have to preset it before the clock gets here for this signal to clock into the D. Sorry, I'm kind of laughing because this is all over the 80s, okay? This is totally asynchronous. But you know what? It works because everything in 1980 depended on this kind of circuitry right here. So this part of the schematic is the successive approximation register, the SAR. It also is used to control the timing for the 3 sample and hold signals. Mux A, which is the A to D sample. Mux B is output on left channel, and Mux C is output on right channel. So I'm just going to zoom in here a little bit. So the successive approximation chip is from AMD, and it has its own output bus. We have a set of tri-state buffers to split it from when we're going to use this bus to come into the DAC to drive the A to D signaling, or coming into the DAC so we can output our audio samples. So that's what this set of buffers do. The SAR is a clock system that comes from the 6 megahertz clock through this flip-flop. So it's essentially running all the time in the background. What happens is that when it's time to do an A to D conversion, the SAR starts to run when it gets this address decode here on the D input, and the SAR will then run, and it starts setting these bits and looking to see if ADC comparator goes high or low based on if the guess from the DAC is high or low. When it runs through all 12 bits, it asserts conversion complete up here, and conversion complete then is used to control the mux timing up there. The way that it knows whether it's going to be doing an A to D or a D to A, again, it's all controlled by the offsets set into the code, and it's always at the same location in every block of code. The last portion here is the DRAM and the DRAM controller. The DRAM is 4 chips. Let me zoom in for a second. So it's 4 16K by 4 chips to make 16K by 16. DRAMs have multiplexed address lines. This particular one has 8 addresses that are multiplexed 2 ways. One's called the rows, and one's called the columns. So we have a RAS and CAS signal, which is asserted low when the addresses are for the rows and columns. So what do you mean by rows and columns? That's just how we do a reduced pin count. The memory array in here is just simply accessed twice instead of having all the address lines, again, to reduce the pin count. So we can have up to 8 rows and 8 columns, which would be a 64K RAM, but these are 16K, so we have 8 rows and 6 columns of addresses right over here. In order for the DRAM to work, it's called refreshing the DRAM. It depends on the DRAM technology. Usually it's on the order of 2 or 4 milliseconds of refresh time. And what does refresh mean? It means that there's internal capacitors in here, and we have to address all of the rows in the refresh time to keep the capacitors charged up with the internal charge pumps. So the rows are considered the lower byte of the address and the columns are the upper byte. So as long as we address every single row in the memory in the refresh time, the data will not be lost. Now, in many cases, like the standard computer, you can't guarantee that's going to happen depending on what you're executing in the code, so that you have external refresh circuitry that's running in the background that makes sure that the RAMs are always refreshed. However, in cases like this, and also very similar in video cards, where you have this thing is the hardware is running all the time, that's not a problem. So there's nothing specific in here that says we're going to have to force a refresh address. It's going to automatically refresh because we're running through the DSP code fast enough. Remember, there's 256 instructions, and that's 256 counts, which is 8 bits here. So as long as the instructions are running, the RAM is running. Again, you're going to also see that same kind of thing in a graphics card, which means as long as we're going across a horizontal line, we're going to refresh all of our rows of memory. There's 2 sets of multiplexers here for the row and column addresses right here. So the addresses come in first through the rows. Remember the RAS and CAS timing from the other page, and then it switches over and does the column addresses. That's pretty straightforward. The only thing here that's kind of unusual, if you look, is what in the world are these 2 adders doing in here? What does adding something together have to do with accessing the memory? And the answer is, this is how Keith Barr did multiple circular buffers in the memory. So there's the standard way to do it, which is if you had a general purpose processor and you had lots of internal scratchpad memory or lots of internal registers. If you wanted to have 8 different sections that each is a circular buffer, you could have 8 pointers, and then you could increment those pointers in the code and things like that. But he did not do that. What he does is he has offsets, and every instruction in the DSP code has an offset, and that offset is pointing to the start of his circular buffers. And so let's say that you have 4 buffers in memory. You would have 4 offsets, and the offsets are constant, so you can say, well, I'm going to put them 2K apart, for example. And then as the code executes, the accumulators make sure that the addresses always increment by 1, but the offsets are constant. So imagine these 4 sections of memory are sliding in time from the start to the end of memory by the end of the instruction loop. So they all slide together, and each time they slide, the offsets are added by these 2 chips right here. We'll talk about that a little bit more in the software department, but I thought that was very unusually done. And again, it's a very minimal design because he didn't want to add complexity to the DSP engine. So he has enough width. Remember, there's only 4 instructions. It's only 2 bits. in the instruction word, he reserves the rest of it as an offset. So every single time he wants to go to memory, he adds the offset, and that's what uses to address it. Well, that concludes our discussion of the schematic of the Midiverb. I hope you enjoyed it. And did you catch the little exclusive OR gate here? There it is. Our next video will be on the software. It will come out in about a week from this was being published. It's going to be a quick overview because I'm not the DSP coding expert. That's Eric. So Eric prepared the slides, and I'm going to present the slides, and hopefully they're enough detailed, because to really understand all the coding, it's hours and hours of explanation. But I'll give you a brief overview, and as my professor liked to say in college, the rest of it is left as an exercise for the reader. See you next time.